Okay, so let me start the timer. I'm Roberto Parisella from Simula UiB, and I will present this paper on knowledge-soundness of plonking ROM from falsifiable assumption. This is a joint work with Elger Lipma and Jan Nosim from the University of Tartu. And it's the third paper of a line of work when we were trying to tackle this problem. We apparently did. So the talk is divided into three parts. The first one, which is actually the longest, I will give you an intuition on how Plonk is defined, the limitation of the previous security proof, and I hope I will make you understand why a new security proof was needed. Then I will talk about this first intermediate result on the security of the linearization trick, which is a well-used optimization, a well-known optimization for snarks. And lastly, I will explain how we managed to prove the knowledge-soundness of Plonk. Okay, so Plonk is defined in the original paper, starting from a very ideal protocol and compile into several steps to get a final snark, which is very optimized and very efficient. So I will follow this pattern to explain how it is. So let's start with the ideal version. We have an indexer, which is a third party that makes available a list of public polynomials. Then we have a prover, which has a statement X and a private witness W. And we have the verifier, which has, of course, only the statement. The provers send polynomial oracles, ideal polynomial oracles to this verifier. The verifier replies with some challenges, many rounds of this interaction. And then the verifier checks a verification equation, which has this shape. So we can image those as J's as public multivariate polynomial, which are evaluated into the polynomial oracles and the indexer. In the end, we get a univariate polynomial, and the verifier check if this polynomial is the zero polynomial, and in case it accepts. We want the standard properties, completeness, knowledge soundness, zero knowledge, and we require succinctness, which in this case for Plonk means constant communication and verification complexity, so independent of the size of the witness. And those properties has to be preserved during the compilation, and the final Plonk will have this property. Okay, so towards the real Plonk. First, we weaken a bit the verifier. Now the verifier doesn't check polynomials, but instead sample a random challenge, evaluate the last polynomial in the challenge, and check if this evaluates to zero. And of course, since this challenge is sampled independently, without probability, this verifier still will catch a malicious prover. And in order to explain the next step, I will have to introduce the notation for cryptographic groups. So we use additive notation, which means that we consider abelian groups of prime order P. 1 in bracket is the generator, X in bracket is the element of order X. We suppose some hardness, for instance, a discrete logarithm, the CDH, the SDH. But to give you an intuition, like for these groups, let's think of adversaries that receives this group element as an input. So group element of order sigma evaluated in various power, output some group elements. The intuition is that if the output is like a linear combination of the input, which in this case means an evaluation of a polynomial of degree up to n in the secret trapdoor sigma, then this is an easy task, and any party can do that. If actually this output is an evaluation of a polynomial of degree up to m, this is hard, and parties shouldn't be able to do that. And the same if some party try to evaluate a proper rational function. Very intuitively, the first is some variation of the CDH assumption, the second is some variation of the SDH assumption. Both these tasks should be hard. Okay, we require some more structure. We actually take 3 of this group. They have prime order. We define this pairing operation to map the element of order X in group 1 and the element of order Y in group 2 into this element of order X times Y in target group. and we require like the standard no existence of efficient isomorphisms. Okay, in these settings, we can define the famous KZG commitment scheme. This slide would probably be a bit technical, but bear with me. I guess many of you already know this scheme. The commitment key has, of course, this shape that I presented before. There are group element of order sigma in various power, and then also 1 and sigma in group 2. The commitment is just the evaluation of the polynomial in the traptor sigma in group 1. The opening phase, well, we want to show the correctness of this evaluation, so of the fact that f of alpha is equal to eta, which means opening the commitment at alpha in eta. We define this function hx, and the proof will just be the evaluation of this function in the trapdoor sigma. Yes, this function is defined as a rational function. The verification is like it has this simple form. You can easily check that if the prover is honest, this verification will go through. But why this is secure? Well, the point is that this hx, that is in general rational, is a proper polynomial if and only if the prover is honest, so if eta is the evaluation of f of alpha. And in this case, the prover can actually compute the proof without breaking any hardness. Otherwise, this proof will be a rational function. This is supposed to be hard for the SDH assumption, and this is, of course, shown in the original paper implying evaluation binding. Okay, we use KZG for defining Plonk. Now we have a proper SRS with a public indexed polynomial. This SRS will contain commitments to this polynomial and, of course, a commitment key. The prover now, instead of sending polynomial oracle, send commitment to the polynomial that the ideal prover would have sent. The verifier sent challenges, many rounds of this interaction. Now the verifier sampled the evaluation point, but gives this to the prover. The prover computes the evaluations of the polynomial, compute openings to show the correctness of this evaluation. Send everything to this verifier, and the verifier will check the correctness of the opening and will check the validity of the verification equation. But this is not exactly Plonk because on top of that we need to apply some optimization to make this protocol very efficient. Probably the most important optimization is this linearization trick, which can be done when the verification equation has that particular shape. So we divided the polynomial sent by the prover into two sets, the green polynomial and the purple polynomial. Intuitively, the green polynomial are the ones that are inside of Sj, while this purple polynomial are just multiplied outside on each hard end. Okay. If the verification equation has this shape, we can do some optimization. In this original phase, the prover, as before, will commit to both green and purple polynomials. The verifier sends the evaluation challenge. The prover computes the evaluation of only the green polynomials, but not the purple. Of course, compute the opening proof. Now, the prover defines this polynomial, which is defined evaluating the green polynomial, but leaving the purple as they are, and compute an opening proof to show that the polynomial hx open at psi in 0. This will save to the prover the burden of opening all the purple polynomials, and it's a very important optimization that is used in many snarks. So the prover now sends all these openings and the evaluation of only the green polynomials. The verifier will check the correctness of the opening, will homomorphically reconstruct the commitment to this purple hx polynomial. and verify that this polynomial is 0 in the evaluation point. This is equivalent to the previous check. And there is another optimization that makes this scheme very efficient, which is the possibility of batching together openings. Here I will just show a simple example where I want to batch just the opening of two polynomials. Everything is the same until this point, but now the prover will only send evaluations and not opening. The prover will receive an additional challenge and use this challenge to batch together the two openings. Send back the one single openings, and with these verification equations, the verifier can check in one single check the correctness of two openings. And it is very easy to see that this can be iterated, and in fact, with this process, the prover will send one single opening for an arbitrary number of openings, and the verifier will check all of them in one single verification. And yeah, this is basically how Plonk has been defined. So there is this initial stage, prover verified interact, they get the commitment from they get commitment to both green and purple polynomials, send evaluation challenge, receives evaluation of green polynomials, sends batch challenge, and receive a single batch opening to check all the openings together. Okay. What I described before is actually a methodology that is true for Plonk, but is a little bit more general. It is this general tool of taking an idealized proof model, which in Plonk they choose these idealized low-degree protocols, taking an extractable commitment scheme, and define a succinct argument. And what I don't say is that in order to define a snark, they need non-interactive, but this is standard because they just take the Fiat-Shamir transform that we've seen yesterday and they define a snark. And this is a very successful partner. However, it has some problems, at least in this case. To show that KZG is extractable until very recently, we need idealized cryptographic groups such as AGM or GGM. To show the security of the Fiat-Shamir transform, we need an idealized group, which is the random oracle. So the security is quite problematic because it relies on two idealized groups. Even worse, the security of the KZG was actually relying on a usage of the algebraic group model, which does not translate in security in the standard model. And let's see why. Basically, the KZG extractability, how was it done until very recently, was implicitly or explicitly based on this knowledge assumption. We give to the adversary a KZG commitment key, the adversary output a group element, and we suppose the existence of this AGM extractor that just compute the coefficient of the committed polynomial. So this is a very powerful extraction because it says that we can extract the committed polynomial exactly at the moment the adversary output the commitment, but before we see any evaluation or opening. And the Plonk security was actually based on this assumption, but not only Plonk's, other schemes as well. However, adversary in the standard model can do an operation which is oblivious sampling, which consists of sampling group element without knowing their discrete logarithm. So, for instance, they can take a seed from a super polynomial mean entropy distribution, a uniform seed, for instance. They can encode this seed using some very nice function into a group element, such that recovering the discrete logarithm of this group element, even knowing the seed, is as hard as solving the standard discrete logarithm. For instance, an example of this encoding is those class of family encodings on elliptic curve. And this results in the fact that, as we show in a previous work, extraction from the commitment only does not hold in the standard model, and therefore this AGM in the Plonk proof was used in a way that does not translate to security in the standard model. So last year we make a first step. We proved that KZG is extractable in a more with a more reasonable definition under this IRSTH assumption. And we proved that with this notion of extraction, we still can prove the knowledge soundness of Plonk. However, we were not able to prove the knowledge soundness of the optimized Plonk. Particularly, our previous version didn't include batching and linearization trick, and resulting in a snark that was not exactly practical. As you can see, particularly the verified complexity would be quite bad compared to the real Plonk. And there is also another issue. When we use the Fiat-Shamir transform, if the starting protocol is knowledge sound as the original Plonk and as our previous Plonk, then we have a loss in the Fiat-Shamir security, which is Q to the mu. Like Q is this, we can think of Q as a bound on the prover, like the number of queries that it can make to the random oracle, and mu is the number of rounds of the protocol. But this loss is actually usually ignored in implementation. In implementation, they assume a loss that is linear in Q, which only holds if the original protocol has stronger sound property, like this special soundness, as shown in this other paper. So there is an important open question to see, for instance, if Plonk is special sound and if this loss, linear loss assumed in implementation holds is provable secure or it's only heuristic. Okay, and with this in mind, I hope I can give you enough motivation. Let me check my time. And we can get back to we can go to the second part of the talk, which is try to solve this subtask and try to argue something about the knowledge soundness of this linearization trick, which is the most challenging optimization that has been used in Plonk. Well, what we know about the linearization trick security, which I recall can be used when the verification equation has this particular form and consists of not opening the purple polynomial, but instead opening this hx polynomial and say that this hx polynomial open to 0. Well, the linearization trick is secure in AGM, of course, but this security does not translate into security in the standard model. As shown by our previous work, and the attack is actually discovered independently in the same time by also Fiore, Faonio, and Russo. Those authors were able to show that the linearization trick is knowledge sound in the algebraic group model with oblivious sampling, which is a more realistic algebraic group model, closer to the standard model, but only under some conditions on the purple polynomial, so not the general case. Very well. However, our first result is a negative result. We showed that the linearization trick is not special sound in the standard model, even if we restrict in the case when knowledge sound holds in Agimos as shown by Fiore, Faonio, and Russo. Particularly, we show that if the discrete logarithm assumption holds, then special soundness is impossible for the linearization trick, which implies that knowledge soundness is impossible. And now you may be wondering, okay, but wait a minute, we have a protocol that is knowledge sound in AGM, not knowledge sound in the standard model, and knowledge sound in Agimos. How this is possible? This seems a very contradictory things, but in fact it is not. And this is because knowledge soundness in ideal model is inherently a non-black box technique. So here, for how they are defined, the extractor in these ideal models, they see adversary code, they see adversary random coins, and this is what makes extraction possible. However, extractor in the standard model, they are black box. And in this, particularly, they don't see the random coins that the adversary used during the execution. And this is what makes special soundness impossible in the standard model. And this seems like the end, because Plonk used linearization trick, and linearization trick is not special sound, so Plonk is not special sound. But does really Plonk use linearization trick? Linearization trick is defined for verification equation that has this form, where green and purple polynomial are both polynomials that are committed to by an untrusted prover. This is not the case for Plonk. Plonk verification equation has a shape that is more similar to the one on the left. There are some addends. Here I highlight one, but it's the same, just for simplicity, where the polynomial that is external to this multivariate S is not a purple polynomial, in the sense that it's not a polynomial committed by an untrusted prover, but it's a polynomial that is it's an indexed polynomial, so it's a public polynomial committed by the trusted party, and particularly known by any party and known by a potential reduction. So the hx defined in the case of Plonk has this shape, which means that some of the polynomials in this hx are public, and they are again known by parties. And this is what saved Plonk security, and what makes us possible to prove that yes, Plonk is special sound in the standard model. In order to do that, we kind of rediscovered a technique that came out of action that we called RENO, which stands for reduction to a hard assumption if not polynomial. I will try to give you an intuition on this technique. So let's say that Plonk verification equation has this simple shape. I just take two addend to make it very simple. In one addend, the unopened polynomial is a purple polynomial, which means it is sent by an untrusted prover, and it is committed by an untrusted prover. In the other addend, the unopened polynomial is public. Okay, let's say now that we have an adversary that receives a commitment key, will output a bunch of polynomials that we interpret as green polynomials, and commitment to one polynomial that we interpret as the purple one in this verification equation. And let's say that the output of this adversary satisfies this verification equation. Okay, if this is the case, we define this d of x as the rational function here in the slide. If the adversary is successful, then the committed value, d tilde, is equal to the evaluation of that rational function at the traptor sigma. What happens now? Well, if t of x, which is in general a rational function, is not a rational function, but for this choice of green polynomial is happen to be a proper polynomial function, then it's fine. We have extracted the polynomial committed in d tilde, even if d tilde has never been opened. If t con x is not a polynomial, well, then this adversary has compute a proper rational function. And remember, this is supposed to be hard because it's a variation of the STH assumption. So with this intuition in mind, we were able to prove that the interactive Plonk is special sound in the standard model. How did we do that? Well, we started by extracting all the green polynomials that are the ones that are properly opened during the protocol. This was possible following our previous work using the same technique. And we just need to show that batching all the proof together preserves special soundness, which we did. Then, using this RENO technique, we extracted the unopened polynomial, the purple one. This split RSTH assumption is essentially a variation of the RSTH assumption that sort of distill this RENO technique for the most general case. And it's a computational falsifiable assumption. And lastly, we show that the idealized model for Plonk is itself special sound. So once we extract all the polynomial, we have a trillion transcript for the idealized protocol. Very well, we compute a witness because this idealized protocol is special sound. This is the first time that actually an idealized proof model is proven special sound. And as a consequence, this means that Plonk is tightly knowledge sound in the random oracle model under the RSTH and the split RSTH assumption. Okay, so this is the end of my talks. Thanks for your attention. Like, those are the papers that I've cited, and I will happily take questions.
Any questions? Where's Giacomo for a good question?
There is a question there.
Yeah. Oh, Ariel, good.
So you said that the index, the pre-processed polynomial saved you, but I remember, I'm not sure from what paper, but reading that what saved them was that the polynomials are n independent. Can you comment on the relation? And
this is exactly where it is, the slide. Yes, it's exactly this important remark. Like the other paper where they have this independence, they were okay because they were proving knowledge sound in some idealized model. And this is a notion that is inherently non-white box. So in those cases, they had extractor that sees the random coins of the adversaries. And this makes our reduction not working. While in our case, we are proving special soundness in the standard model, which is defined as a black box notions. So our extractor doesn't see the adversary random coins that are used for for computing the output, right? And in this case, even this linear independence doesn't really help. So the point is that the linearization trick was, as defined, was kind of an overkill for Plonk. You need this less powerful protocol, while some addend are have polynomials that are like public. Or if you prefer to interpret in this way, some of the purple polynomial are the constant polynomial 1. Still the same.
so the one with the n independent, it wasn't in the AGM-OS, it was only AGM. Was that the difference?
It was only AGM, but it was for simulation sound, and they say it translates to knowledge soundness in the AGM-OS. But still, in those two models, extractors are white box. And this is the crucial difference.
Right, okay. Thanks.
More questions? Okay, so let's thank the speaker again.